baby all, how you doing? Talking about some stars or gravity today. I'll see who shows up and perhaps take suggestions if anybody would like one or the other or both. And yeah, well, actually everything looks good, I think. Uh as usual, let me know if I could adjust my volume at all. Looking good at the moment. Uh, People come, I'll mention how I was looking at that debate that PhD Tony had. It's always good to see PhD Tony. He always shares some good stuff about science and calculations and so forth. Awesome, Lisa. Glad the volume is good. How you been doing? Hopefully everything has been good. And by the way, you can let me know if you'd like to hear about Praesepe, uh, Kepler's laws or leading up to it, or both. I could do half and half or talk more about one. Yes, I saw that fact the Flat was going over the debate. But I was actually preparing for this stream here, so maybe I would have deferred or something if I knew he was going to do that. But it's a good debate to review, I'm sure. Maybe I'll catch the rest after this stream or something. Awesome. What do you want to? Which one you want to start with first? I'll start with that one first. See a few more people join. Be sure to chat. Let me know you're there. Sounds good. Well, I have hmm, Central Forces up, so why don't I start with that since that's up on the screen there? And so basically, what's going on is Kepler's laws. Like I spoke about Kepler's laws before, I'm pretty sure. And as a reminder, Kepler's laws are basically so basically Tycho Brahe did some what must have been immensely specific observations of the motions of the planets. So accurate, in fact, that after he died, and Kepler, I guess, was sort of his understudy or student or employee or something like that. Kepler got a hold of that data and analyzed it and divined the motions of the planets. And he discovered these three things primarily, uh, in no particular order. I might be mixing up the exact order they come in. But one is that the planets go in orbital in an ecliptical fashion. So before him, people thought that the solar system was somehow divine and the most perfect shape is a circle, so everything moved in circles. What was really going on is the Earth and all the planets are going around the sun in an ellipse, and the sun is one of the foci of the ellipse. So this is one foci of the ellipse, this is the other one. This is an exaggerated version because the ellipse is almost a circle. There's something called eccentricity, where basically if eccentricity is one, it's a perfect circle, if I'm remembering right. And the lower the number is, like technically, if an ellipse is zero, it's an infinitely long ellipse where it's like perfectly flat. And if it's one, then it's a perfect circle. So like our revolution around the sun is like 0.98 or something, or 0.99. It's out there very close. But suffice it to say, he realized that the motion of the Earth and all the planets was an ellipse. And looking down, we're going counterclockwise. And the other one is going to be the period squared equals area cubed. And what this means is the period of the orbit of a planet, like for instance, Earth, the period is 1 year. If you square that value, is going to equal the semi-major axis of the ellipse that the planet, Earth or whatever planet, has around the sun. So if you look at this ellipse here, this is the major axis going horizontal. This is the minor axis. So the semi-major axis is this, so this will be A. And the period will be how long it takes to go around the sun. So for instance, the period of the Earth is 1 year, and the semi-major axis is 1 AU. That's how we defined it. And of course, 1 equals 1. And you can do this with any planet, and you'll get the precise fraction in astronomical units. AU is astronomical units, which means the average distance from the sun. You can get every distance of all the planets in astronomical units. At least it says circular orbit equals 0 parabol. Okay, I had it reversed. Thanks. I know that we're like close to perfect. So awesome. Thanks for that correction. So basically, what we're looking at, and I'll list the last one before we go to the more complicated stuff. So the last one will be if you take this ellipse and you plot any 2 points in the orbit over the same period of time, they'll sweep out the same amount of area. So even though they might be at different parts of the orbit, if you track the same amount of time, so basically it'll be going slower out here because it's farther away, and it'll be going faster here because it's so close. And each of these areas will have the same exact area. If you take the same amount of time, so that's the third law. Also, yeah, it's easy to mix that stuff up. I remember on the exam, well, I always study right before the exam. So the class that I learned most of this stuff in, I got an A in that class, but it was like last year. But now we're starting to do it in, I can't say a deeper way, but a deeper derivation, as we can say. Like in stellar astronomy, that was a stellar astronomy class. We were sort of just given the formula, and we had to like just know which formula to use when. But in classical dynamics, as we'll talk about momentarily, we're getting into the nitty gritty, which is what I was about to go into after I listed the last one. So basically, this is a generic form of Kepler's second law that deals precisely with um, the solar system in AU in years, but this is also applicable anywhere in the universe. It's just that this term here will end up having a constant in the front, and the constant will have like the gravity, the masses. I don't remember off the top of my head, but over the next few weeks or whatever, I'll work towards it again. But suffice it to say, there's something in the front that we multiply this with, where we could, for instance, take two stars and look at their period of rotation, and we can see how far they are away from each other, and we can get the masses of the stars. It's something GM. Now, the thing is, we can't get the individual masses that way. We end up getting the entire mass. It's something that'll be M1 plus M2 up in there, but we can get the entire mass. But if you're looking at a binary system and the two stars are about the same mass, well, one of them is going to be half and half. Or if you're looking at them and you can say, well, one of them is about 3 times bigger than the other one, well, then you know the ratio there, right? It's going to be 1 to 3, dividing up this M plus M. And the same thing, by the way, is utilized to get the masses of the sun and planets. All we have to do is take the period around the larger body, like the Earth around the sun, and we could divide the mass of the sun because the sun is the bigger body. We get the M plus M mass, and the Earth is so small compared to the sun, we just consider it the sun's mass. And similar with the moon, except is more closer to the ratio thing. I was talking about like 1 to 4 or something like that. But that's that. But the process of getting to this equation here with all the masses and stuff is pretty complex, right? So this is chapter 8 of our textbook. And by the time we get to Kepler's laws in detail, that's section 7. So there's 7 different sections leading up to that, right? So what I'm going to do here is talk about like the first few sections. And maybe what I'll do is expand this a bit. Depending on what I'm showing, it fits slightly differently. So let me take the Discord and expand it to make the chat bigger. There you go. And that seems sufficient. All right, so I'll leave it there. So the idea is that we're talking about a motion between systems of two masses affected by gravity by a force. The reason why we do two, I've only heard this in passing, but apparently like the 3-body problem is near impossible. You have to do like some kind of numerical estimates and stuff like that. The 2 bodies is very easy, which is why if you look at this, the Kepler formula is between 2 bodies. So, you could look at any 2 bodies, like any planet in the sun, and get the period easy. But if you want to calculate like the entire solar system at one time, that's pretty hard, right? But we could usually break things down into 2 bodies affected by a force. They call it a central force, which means that that force is pulling these 2 bodies toward each other along the center line of their masses. So common aspects of this is, like we were discussing, motion of celestial bodies, planets, comets, like how we know how these comets is coming around, how we know planets are coming around, and so on and so forth. Sure, it works for galaxies as well, but when you get to more heavy masses, it starts to become more and more of an estimate because of relativity starts to play a part. Or even 2-body nuclear reactions. Apparently, before we understood quantum mechanics, this same dynamic was utilized for instance, the calculating the revolution in a revolution in the classical sense of an electron around the nucleus of an atom. Of course, that's only an approximation because now we know the electron is a sort of a more like a field than a little particle going around, but still is a good approximation. So when you collapse a wave function, it behaves in a similar way to a particle, though it still outputs wave-like results. But one day I'll have a quantum mechanics stream, maybe next week. But that's that. Now, what we end up having to do is have something called the reduced mass. And we won't get all the way to the reduced mass, but we'll get to the equation that leads to it. So the symbol for reduced mass is basically mu. So basically, it's a way. I was speaking of how we can have a little constant up in here uh, to calculate these group masses. And there'll be some other stuff in there, but it'll be M1 plus M2. The more accurate way of doing that is with the reduced mass, right? And the reduced mass is basically taking the 2 masses of the 2-body system and putting them into one unit to allow us to more easily work with the equations. Again, similar to how it's done with Kepler's laws. Now, when you have 2 particles, you always need 6 quantities. It's almost like you need so many unknowns for an equation you're trying to solve. So one way is simply the 2 vectors of the thing, right? So if you look at this, I have 2 vectors pointing to a thing. And so basically, if I had an origin, I didn't draw this one out because this is the simpler case. But let's say you had an origin here, and you have a body that's going there, to be my R1, and then you have a body that's going here, this is my R2, and basically I can use these 2 vectors to describe these 2 bodies. I can get the velocities of the bodies with those vectors. I could describe the whole system with just those 2 vectors. That's one way to do it. Another way to do it is to consider the center of mass vector to be its own thing, which has 3 components. And then consider this equation to be the other three. So it still has six components, but now in a sense the the six components are more interrelated amongst the two bodies rather than being more separate as in the first case. Yes, they did. Now remember though these formulas for atoms are an approximation. And this is actually one of the things that the flat earthers get wrong all the time. I could just make this a side on that. But if you look at an electron, I mean, electron does have mass. I don't remember what it is off the top of my head, but it's something like 9 point something to the 10 to the negative 31 kilograms, or something like that. I know that's not the exact amount, but it's a bit off. And then if you have the mass of a proton, it's going to be a whole lot bigger. It's going to be something like, I don't know, 8.5 times 10 to the negative 26 or something. Again, these numbers are off, but it's something like that. So you can model an atom like the proton is here and the electron is moving around. And you could actually calculate the force of gravity between them. So the force of gravity between those would be the gravitational constant, ME, MP over R squared, which is the radius between them, which is basically the half the size or diameter of the atom. So you could examine the atom and see its diameter and take half of that. We have to do this for one of my classes or something similar to this. And then the direction between them. F, G, M, F. So that's that. And you could also do the Coulomb constant force, which will be the K and then Q1, or I should say QE, QP over R squared, R hat. And this will give you the force from the electromagnetic charge between them, because this is basically a negative, well, not basically, it is a negative charge, and this is a positive charge. If you look at the talk I had with Ross, you'll see he showed this and had no idea what it was. I asked him, and he didn't know. Yeah, but he just didn't know at all. He just, you know how to just bandy stuff in memes. Just like how Flatzoid did, why he couldn't give any sort of uh, second law of thermodynamics explanation. You can just repeat the meme. But if you compute this, you'll find that the electromagnetic force is a lot bigger than the gravitational force, which is where the old electromagnetic force is so stronger and stuff like that. But it's just that on a larger scale, so on a small scale, you have a very direct uh, uh, positive and negative charge pulling on each other in that respect. Uh, so the effect is more, the positive and negative electric force is much more potent. Uh, whereas on a larger scale, like if we have a human, we're not magnetically attracted to everything because all of our positive and negative charges are balancing out in our body. So therefore, on a larger scale, the electric force takes much less precedence than gravity because all of it balances out, right? It's not really doesn't really play a factor. But on these larger scales, I mean, what's going to balance it out? You just have a hydrogen atom. That's what a hydrogen atom is, just a proton and an electron. So the electric forces are going to be playing a major part because there's nothing to balance those forces out. And thus you have the electric force being much bigger than the gravitational force because of that reason. But like I said, though, if you actually apply this fully to the extent that we understand quantum mechanics now, what'll end up happening is if you have this electron and proton, any orbit is going to be losing energy because we know that if you hit an electron with energy, it's going to radiate that energy off. So electrons want to seek the lowest state. So if this thing was really rotating, what will happen is it'll just continue throwing energy off and it'll eventually crash into the proton because again the electric force is so strong and then we won't have any kind of complicated or complex matter because basically all the electrons or protons will collapse and probably become neutrons and you just have a universe of neutrons. So we have to figure something else out to figure out what's going on, and that's how we get into electro like quantum effects. But again, it could be approximated if you ignore the fact that in reality it would just fall into it if we only looked at it classically. But it could be approximated. They used to do that back in the day, but they couldn't get anywhere near the precision that we have now where we can build like quantum computers, right? You can't build a quantum computer with subatomic particles using Newtonian mechanics. It's just not going to work. So there's some fun stuff, interesting stuff. Now, another way to look at it is going back to the large scale is to consider the idea of so basically, let me go back to the first diagram. This same dynamic of the R being its own thing, the big R, and the big R is this vector here. So the big R is basically going from the origin to the center of mass. And then the little r's are the same vectors as before. One is going to one mass, one is going to the other mass. But now we outline this third vector, which is going to be R1 minus R2. So basically, if I take R1, which is the one on the going up right here, and I subtract R2 from it, then that's going to be this vector going that way, right? And if there's any questions, let me know. But that's how we get that vector. And this is how apparently we normally do it because this is the one that the book focused on. Now, if we want to get to reduce mass, it's some ugly algebra because what ends up happening is there's something called a Lagrangian. When you get to complex uh, uh, systems like celestial bodies, it can become difficult to get the equations of motion. So you can use a process that was formulated by, you guessed it, Lagrange, and get the Lagrangian. There's also a Hamiltonian way of getting it too, but even the Hamiltonian is based on the Lagrangian, where instead of going directly to the equations of motion, you get the potential energy, which is this, and you get the kinetic energy with this, which is this, and you could do some manipulations on the kinetic energy and potential energy, and get the equations of motions that way. So that's what we learned to do last chapter or two ago, whatever it was, to get the Lagrange, and they're kind of fun. I kind of like them. Um, I took part of this class before, and I didn't really get it then. But I took some time to take some other classes and come back, and it's actually not that bad, right? So what we're going to do is, so actually I put the Lagrangian together here. So the Lagrangian is going to be the kinetic energy minus the potential energy. And we have two bodies, so the kinetic energy of one is going to be our simple 1/2 mv squared, which can simplify to 1/2 x dot squared, the derivative of x squared. And we could also put it into terms of the system that we're working with, which is radius out from the center of mass. So that becomes the velocity, the kinetic energy of particle one is that 1/2 of that mass times the change of this radius. Because as we go, around the planet, around the sun, that's kinetic energy we're moving, and our radius changes a bit as we go around, and not even if the distance changes, each time its direction changes. It's a different vector. So all of this includes the changes in vectors when the vector gets longer and shorter, or when the vector is pointing in a different direction, right? So that R is really a vector that's also a function of time. So we're looking at this right here, a vector as a function of time. So I plug that in, and it's easy to get the Lagrangian, and it's a whole other process to get the equations of motion, which is down the line. Thank you. Thanks for letting me know, Lisa. And if you ever have any questions, let me know. So the median step between getting the equations of motion is working towards the reduced mass, because again, we want to try to find some simple thing we can plug into an equation and just have this sort of one constant that's going to represent the masses that we're working with, right? And eventually we'll look at specifically that for the uh, uh, those laws. To give me a few weeks for us to work towards it. Now, what we're going to do is we're going to work with this equation, So recall that when we made our system, we defined this to be the case. I'm picking out this vector. So R equals R1 minus R2. And we also have uh, this vector addition right here. So all I did here was I just took this vector M in R1 and I added it to vector M in R2, and I call that R, our resultant vector. So we're just putting those things together, right? So we have a vector addition term right here, just adding these vectors together. And by the way, the reason why that's 0 is because when I put it in this frame, and the odd thing is we can sort of move back and forth between these. So we're kind of using this relationship here from this first one, R equals R1 minus R2. And we're also using the fact that in this system, the center of mass vector is 0 because we eliminated it. We're just focusing on the two masses, but we can do the same thing. And if we add R1, which is this, to a negative R2, which is going this way, we see that we get a long R, which makes sense because the center of mass is closer to this mass, which means that mass is bigger. So it's going to be pulling that planet towards it, which is why we orbit the sun and the sun doesn't orbit us. Because when we add these vectors together, this negative R2 will make that R1 long in this direction, and thus we're being pulled towards the sun. And Anthony says, where is our location in the Milky Way? Our location is towards the outskirts. So if this was the Milky Way, we would be about here, somewhere towards the edge a little bit. And we know that because, like for instance, when we look at the CMB, if you ever look at a CMB image, you'll notice there's a sort of shape in the middle. We have to actually extract out the center of the galaxy. That's one of the things that we have to do. And even on the other side, we have to extract out, there's a little arm going by us. And there's other ways that we know we're situated. And this is not exact, but, give me a little bit of an error margin. It's like somewhere like that. But we'll be more towards the outskirts of the Milky Way, right? And we can see that when we look into out into the universe and into the galaxy. For instance, we have to look inward. In one of my debates, I believe it was the one with Whitsitt, I showed an image of the stars rotating around the center of our galaxy. And we had to look in a certain direction to get that picture. It's like we have to look in a certain direction to look at Andromeda. So, we have several different things that we can look at and place ourselves where we are in relation to each other. So that's about where we're at. Now, this problem here doesn't take that into account because the fact is everything is pulling on everything else. But those things are so far away and also surrounded by other things in other directions that the effects are very minuscule, at least on our scale, right? On the galactic scale, Mercury and Andromeda are like racing towards each other on a galactic scale, but it's going to be like millions of years before they finally collide. But on our scale, the milk, I mean, technically it is slightly, but the sun definitely has more perturbation on our orbit than Andromeda galaxy. The center of mass is literally the center around which they rotate. And I know it seems odd because I'll delete this momentarily. When we normally think about an orbit like the sun, for instance, we normally think of the Earth going around the sun. We think normally like this. But what's really happening is there's a center of mass that's inside the sun because the sun is so close. So let's say that the black dot is the center of mass of us and the Earth. So the Earth has a mass, the sun has the mass, the sun is really big. So this is the center of mass within the sun. And let's say that the red dots are the center of that body. So that's the center of the Earth. This is the center of the sun. So what really happens is the Earth does go around like that, but the sun actually goes around like this. They actually go around each other, right? It's just that the sun is so massive that the center of mass of our two respective bodies are literally in between each other. But when we see things like other stars, like I was mentioning binary stars earlier, and you're looking at two binary stars orbiting each other, like Sirius A and Sirius B, we can clearly see, and of course Sirius A it's still heavy, but it's like a white dwarf. So one of them, Sirius A or Sirius B, I forget which one. We can clearly see that the center of mass is like in between here, and they're both basically orbiting around that center of mass around each other, right? So we can clearly see that when we look at other bodies that are more uh, similar in mass to each other. So this center of mass is literally, if you were to take the mass of these two bodies and divide it in two, this would be the center point between that average mass. And because M1 in this case is bigger than M2, that center is going to be leaning towards M2, towards M1. So that's how that works, right? And what we're going to do is we're going to use the fact that we've called that center of mass 0 to go ahead and add these two vectors up, which is going to be M1 R1 plus M2 R2. And of course, if we look at that, there's a vector going there and there's a vector going there. We just add them up directly. And the center R is 0 because they balance each other out. Because if our distance to the sun and the gravitational pull and all that stuff didn't balance out, we would either fly off into space or we would crash into the sun. So we have a stable orbit because these two vectors balance out. And if we subtract one from the other, we realize which one is more orbiting around the other one to balance everything out. We know we're orbiting around the sun more than it's orbiting around us because the center of mass of the sun is again, the center of mass between us again is inside the body of the sun, but we are still orbiting each other, right? And that's how we get there. So you can see why this stuff is so complicated, right? You can see why it can seem so enticing for people to just declare they're right and know better. It's hard. It's hard, man. To really do science and really calculate the motions of planets and predict that stuff accurately. This stuff is hard. It's challenging. There's a lot of variables you have to take into account. So it's no wonder why, people just decide to just pretend like they know and not go through the work, right? Now, what we're going to do is we're going to take a step towards getting the reduced mass, which is again putting both of these masses in the same terms. So I put recall. We recall the thing that formula we made earlier, and what we're going to do is we're going to take these two equations from that, right? So if I take this equation and I subtract, at least I add R2 to both sides, I get this. If I take this equation and I solve for R2, I get that. So all I'm doing is taking that equation and I'm solving. And another thing we can do is, if you see this equation here, I can solve for R1 and I can solve for R2. So all I did was take the equations from our system, the vectors of adding the two vectors pointing to the masses, and this vector of the relationship between these two vectors. It's the same relation here as I showed. It shows that we're getting pulled more towards the sun in the orbit, but it's just easier to see up there. And now I'm going to manipulate these two equations to get towards the center of mass, right? So the first thing I did was, and it took a while for me to figure out how to get this right, but y'all be able to see the sharpened version. So don't think I just did this the first time. I tried to have to do it like 5 times or something. So I got answers, but I didn't get like this. There's many ways to solve for things, and you get the right thing, right? And you can have, you know, 2 plus 2 equals 4, and 1 plus 3 equals 4, and 4 plus 0 equals 4. But but depending on your equation, only one of these is going to make your equation work more seamlessly. One of them is going to be like hard math. You're just not going to believe it. And one of them is going to simplify the math as much as possible. So the name of the game is finding a solution and that's a good thing to leave there, and simplifying it to the point that we find the version of 2 plus 2 or 1 plus 3 or whatever. We find a version that makes our equation very simple. So what I did was I took this version here. I started to solve for this one first. R equals R1 minus R2, which is this right here. And what I did was I plugged in for R1 and R2. So this is my R1, I plug that in. This is my R2, I plug that in. And now I'm starting to solve and simplify. So I simplified this and I put a 1 right here because this was the first stable equation. When I finally figured out what it was, this was the equation I was able to use to figure out the other half of it, which we'll get to. So what I did here was I substituted out R2 because I'm going to solve for R1. I'm going to put everything in terms of R1. So I took R2 and I put it in terms of this R2. So instead of R2, I have R1 minus R. Now after distributing that there, separating this out, then what I did was bring one of these to the other side and I factored. So now I factored out R1 on this side, then I factored out R on that side. And I had to do a bit, you can see there's a little bit of algebra in here, making the denominators the same. So I did a cross multiplication to simplify the fraction. And then what I ended up doing was getting R1 all by itself in terms of R M1 and M2. So now I have this radius, R1, whether it's here or here, and I have it in terms of everything else. So I simplified that. More cross multiplication to get the denominators the same. I had to eventually factor this into its two component expressions. Well, I was able to factor in 2 out of this and get one of those expressions and cancel that out. And after all that algebra, now I have R1 in terms of M2, M1, M2, and R. So this is basically 1/2 of what's going to eventually become our reduced mass. So now I have the first radius in terms of the masses and our overall radius, our overall R. That's a good thing, right? Now, what I did was I had mentioned that this was my stable equation. So I took this equation, I brought it down. Maybe I should rewrite that. I had 1 again. Let me find where I wrote it at right here. So this is still 1, right? And then what I did was the first time I factored out R2 because I wanted everything in terms of R1. I factored out R2, I put in R1 so I can solve for R1. Here I did the opposite. I factored out R1 and put in R2. So the R1 I exchanged it for is this one. R1 is that in terms of R and R2. So I replaced that R1, now I have it in terms of R and R2. Right? And the algebra was similar to the last one, except there was a negative that I had to do. I had to still do factorization. I still had to solidify the denominators to add the different fractions. Still had to factor. When I came here to do my elimination of one of the variables, you can see how this is M2 minus M1, while this is M1 minus M2. They're reversed. So what you can do there is simply throw a negative on it. And if you throw a negative on it, so basically if I have 1 minus 2, if I put a negative on that, this is 2 minus 1. So I could multiply that 1 back in, that negative back in, and then I get 1 minus 2 again. So I just took a negative out. I was able to flop this the right way. And now I have R2 in terms of everything else, but there's a negative on it. And this ends up being the two equations that's going to eventually end up being our reduced mass. Now, if you look at this, you can see that there's m2 divided by m1 plus m2, right? And then there's m1 divided by m1 plus m2. So we're getting closer to what I was saying earlier. Remember, I was saying how we're going to end up with a term that's going to be a m1 plus m2. Where is it? Up here, we're going to end up with a term that's going to be a m1 plus m2 that we can plug into the Kepler's laws and, for instance, figure out the mass of a binary system or figure out the mass of the Earth. That's the type of equation I utilized to figure out the mass of the Earth when I had mentioned in my debate with Witsit, where I calculated the mass of the Earth, calculated the mass of the moon and stuff like that. This is how, because you can get that combined mass, and one of them is going to be either a lot bigger, or one of them is going to be a fraction that you know. You can divine that and get that out. But this is what I got so far, right? So you see how it's getting there. It's getting close. And what I'll do one of the future weeks, I'll continue that process and we'll eventually get up to a reduced mass. Yes, power of not. But notice I don't let them get away with it. They're still just their followers still fall for it amazingly. But like with Flatsoy, he kept trying to divert, kept trying to ask me questions, kept doing all the deceptive, manipulative things they do. That is stuck with, look, are you just going to admit and be honest that you don't know? No, he's just going to keep pretending like asking me a question is actually answering the question, or repeating the meme thing. So amazing. Actually, I took a class where we did the second law of thermodynamics. Nothing they're saying is equating to what you get or what you do when you actually do a second law of thermodynamics problem. It just shows the ignorance of these people that the ones that fall for it. So, but let me go ahead and I'll spend the next 15 minutes talking about one of the scientific papers that I had mentioned. Let's see here. Is it still showing? Sure that. I think I have to ensure it on my window. Put up here. That's what I did. Here we go. So these are some of the papers I've read, mostly in part, one in full. Thanks, Lisa. I'm glad you enjoyed. And still more to go, so stay tuned. So it's a pretty lengthy process, but once you get the process down, or I guess once you get to the end of the process, then you can calculate a whole lot of stuff a lot more easily. Glad you enjoyed it, and I'm glad it made sense. So this stuff is complicated to understand. So again, this is technically my second time going through the class. The first time I was doing the class, I just didn't really have enough time to commit to it because I had another class going on and working a little bit. But this time I have the full amount of time. I made 100 on the first exam. I don't know what I made on the second exam. We didn't get the grade back yet. I'm sure it wasn't 100. But right now I have an A in the class. Awesome. Thanks, Lisa. Appreciate it. I have been explaining for a while, so it's something I really enjoy doing. So which is what I want to do for a living. So I want to be a professor. So thanks for letting me know. And one of the things I'll do is I'm working on, like I had mentioned in my debates, that I'm working on stellar rotation. And what I'm starting to do now is look into the Praesepe constellation, which I have mentioned here before. But now I'm starting to get into more detail. And I was able to get the data. I'm looking at the data. I'm analyzing the data. I'm finding correlations between things in the rotation. So that'll come. So I'm still working on that. I have to learn a lot of coding. But what I want to do is go through at least one of these articles here. Let me pick the review. So this right here is a review article. Very hefty. My professor, who's my mentor, told me I should start with a review article because it gives you a good overview. So this is the first one I started reading when I started getting into the rotation of stellar rotation. It's like let me change the size of this a bit. Oh, awesome. So basically, what they do is scientists they the type of review, the period varies. Might be every year. There was a big one every 10 years. Like if you remember, I did that talk on MC Tuna Channel on dark matter and dark energy. And one of the things I read was a white paper. They do it every 10 years, and it's like the state of dark matter, dark energy. And yes, it's going to be. I think you're going to enjoy it. So I think I finally found a niche that so far I haven't seen anybody mention yet. So, but there's so much stuff to read. That doesn't mean I have gotten to it yet, but we will have to see. But but what this did is like if you look at this thing, the first thing I noticed was, man, they had some hard equations up in this thing, man. They had some equations I had never seen before. Now this one is reminiscent, like temperature effective to get luminosity. I remember seeing something like this. Right, this is basically the Boltzmann law, if I remember the name properly. Look at this. It's ugly. So when I first started seeing this, because I first started just focusing on the sun. Yeah, I admit it is relatively easy, but my mentor was like, "Nah, you gotta do some research. You gotta do some harder. You gotta go hard with it. You gotta do a bit more." So I was like, "Dude, I mean, I didn't tell him that, but I'm thinking to myself, like, dude, I ain't gonna be able to learn all this stuff in time." With the paper I found, though, it was a nice happy medium where I still have to learn some stuff, but it's not like, I mean, I think by the time I get to graduate school, I better figure all this stuff out. Yeah, I mean, like I think this is, yeah, I can't even tell you. But the good thing about this paper is it talks about the ways that we uh yeah, you do say that. But the ironic thing is though, if they ever actually learned to do math and did it, then they would be able to easily see that the earth is a globe. Uh because the earth the universe is mathematically sound. I can use that word application to it. Mathematically sound. So what I'll do, and hopefully I pulled up the right paper. I believe this is the one. Let me see if I can search for what I'm looking for. What is it called? Spectral. I know I meant to get another one. Let me pull up my annotated bibliography. Make sure I pull up the right one. But still, I want to. It's probably why I pulled this up because I want to show y'all what these equations look like. They don't play they rough. But I'll get there eventually, right? I'll get there eventually. Hmm. Oh, I put up the wrong one. Okay, I want to pull up the Hans Myler one. This one. So this one, what it ended up doing was, it went into more detail about how we find uh the rotation rates, right? So as your classes, I'll go through some of that for you, and we can get an idea of a few ways that they do it. So as you can see, this is a massive thing. I didn't go through the whole thing, but I knew I needed to have an idea of some of the basics. So I went and found those basics out. I also found one to uh, explain what uh, I'm actually looking at an entire cluster, and it's not actually it's a bit more complicated than it seems initially. All right, so this is when I wanted to look at light curves, star spots, stellar brightness, detection of stellar activity. But these are some of the ways that they do it. So stellar brightness, basically looking at the luminosity of the star, and they could do this in more than one way. Like they can look at how like if you have a binary system, they could look at a star going in front of the other star, and when it starts to block the light of the star, it preferentially blocks one part of the redshift. Because an interesting thing about stars, they're massive, of course, and when they rotate, they're massive enough that, let's say it was rotating uh, this way, where this side is coming towards you, the side coming towards you is blue shifted, and the side going away from you is red shifted. And when that binary star moves in front and blocks half of it, you can get the blue shift from that side more easily. And then when it goes over there, you can get the red shift of that side more easily, and you can get the speed of rotation. And I says one rotation a day, a zillion miles at the equator. Really? Uh, uh, why don't you pose a cogent question, Eyes? I'd be happy to answer your question. Just pose a legitimate question. Like, what is your question? And I'll try to answer you. Light curves. Now, this is interesting to me because this is what the data I'm using utilize, right? So, stellar activity. So if you remember if you probably don't remember the picture, but I look at it pretty often because I'm like bringing it up and I'm putting it in one of my papers and I'm sending it in my graduate applications as well. But if you look at a star, there's a sunspots on it. When it turns, the brightness of the star gets brighter and dimmer. And the thing about stars is they're so far away, they're like pinpricks, so we can't see the details. But we can see that star getting brighter and dimmer on uh, very periodic scale. Uh, Another one, variable stars, looking at the fact that we can look at how big and how the brightness changes, big and small. And apparently they take that and they're able to divine how the rotation is. I don't know how to do that one yet. Exoplanets, I'll read this one. This is a popular one, I believe. Exoplanets, when I observe it, is exactly in line of sight of the orbit of an exoplanet around its host star. The exoplanet makes a transit during the transition of the exoplanet in front of the parent star. A small decrease in the brightness of the star is observed depending on the ratio between the size of the exoplanet and its host star and the distance of the exoplanet from its star. Usually this variation is less than 1%. So basically they can look at this variation and change when the exoplanet goes in front of it and divine the rotation of the star from that. And it looks like Eyes hasn't come up with a cogent question yet. If you ask a cogent question, I'll answer. If you just saying incorrect stuff, believing that is right or something, yeah, just ask a cogent question. The thing about it is, I'd be happy to try to help some of these people. Oh, by the way, look, somebody was asking earlier about who was asking about the location of us in the solar system. I believe it was Anthony. Yeah, Anthony asked that. So here you go, right here. This is it right here. So we're close to the Orion spur arm right here. You can see there's a Sagittarius arm and a Perseus arm. So as you can see, we're sort of around the edge of the galaxy. So it's interesting. It was good they was able to make this sketch. And of course, they make these sketches based upon understanding. You know, an interesting thing, by the way, if you remember the debate that I had with Witsit, I had showed a spectra of the sun, and I showed the elements in the sun, right? Well, an interesting thing is, like, you notice how, like, if you was to click back to that debate, you'll see how I took a spectra in broad daylight, and you can see if you look at the y-axis, you'll see the intensity was very high. And I took a spectra in heavy cloud cover, and you can see how the overall intensity decreased, even though the elements of the sun still made it through strongly compared to Earth elements, right? When we look at that now, one of the lines that you saw in the solar spectrum is the hydrogen line. The thing is, in space, there's a lot of hydrogen, right? Stars are made mostly of hydrogen, and they form from these large hydrogen clouds that collapse. Well, when they don't collapse into stars, there's this big hydrogen filaments of gas all through the universe. And what happens is when we look at light from very far away, each time that light passes through that hydrogen cloud, some of it gets absorbed. Because the reason why we see hydrogen in the sun, the hydrogen clouds, because there's so much hydrogen. So if hydrogen emits light and hits hydrogen at the same frequency, that hydrogen will absorb the light back. So the farther away we look into the universe, the more light is absorbed. But this is the thing. If we look at different distances into the solar system, we can actually see how the light falls off. And thus we can get a three-dimensional picture of the universe by looking at the density of things falling off. So in other words, if we look at something in this area of the space and we can see it very clearly, and then we look at something one redshift farther and we see a little bit, well, we know there's a dense area of hydrogen here that cut off some light, right? And then we can see a few things farther with no great decrease. And then we see another big cutoff. So then we know, okay, so there's a big hydrogen thing here, there's a lot of hydrogen here, and so on and so forth. And this is how we get the densities of the gases in the universe. This is how we get the densities of how dense galaxies are. All of these things absorb and emit so much light, and it gives a tapestry. And that's how when we look at like the CMB, for instance, or we look at um, I forget what the name of the picture is, but there's a very large scale picture. One day I'll talk about that in more detail because it is a fun topic. But if you, when we look way into the universe, we can actually see this big tapestry, filaments of galaxies, and that's how we get it because we can look and we can see how light is falling off in certain chunks, and we know when it falls off a lot, there's a whole lot of hydrogen, the matter there that's blocking that light off. So it's very interesting. This is very detailed how they do it. I had to calculate some of that stuff, and from my galaxies and cosmology class, and even that was toned down. Even that was toned down. But still, it was ugly, but it was fun though. But but the professor, you know, she like leads this big project where they like this international project where she's like looking in. I forgot what she's looking at, but it's something to do with galaxies. That's why she likes teaching that class. And she like showed a little bit of how they do it, like all the stuff they take into account. I mean, it's amazing how much stuff happens between here and wherever that we look in that we have to take into account to get accurate readings. Let me take a look and see what the remaining questions are. Then I'll close up. Let me make sure I didn't miss anything. So we have the flirt. I'll see if he asks a. Oh, looks like he still didn't ask a coding question. If you want to come on, Eyes, if you're actually interested in learning, let me know. I can bring you on. I wasn't going to bring Juan back on, but he was like, do this first. I was like, never mind. Right. But if you want to come on, Eyes, or anybody else, let me know. I'm in Discord right now. Just nobody's in there with me at the moment, but every time I do this, I'm in Discord. So you can just hop on at any time as well. Uh, but awesome. Hopefully y'all enjoy it. Uh, I'll go ahead and hop off. So we talked today about mostly getting towards the reduced mass. We could eventually do a lot of celestial mechanics. That's what we're leading to, by the way, in class. We get into celestial mechanics where I'll be to calculate the rotations, the revolutions of planets and stuff like that. But it's a long process to get there. Talked a little bit about the rotation of stars. And if y'all have any other topics y'all want me to know, want me to cover, let me know. And anything to do with astronomy, physics, happy to talk about it. And but absent of any suggestions, I'll come with something next week. Glad you enjoy, glad you learn. Always good to have y'all to talk to, chat with. It's a pleasure to see y'all each week. And I look for y'all again next week, same time. Have a good one, y'all.